Hello, everyone. So we are going to have a full lecture in this dynamical system session in this afternoon. And maybe we will witness the strengths and also diversity of dynamical system theory in South America. Okay, and the first speaker is Andrés Navas from Santiago, Chile. And his achievement was well known in topological study of low-dimensional dynamical system, especially in that of group actions. So, and now he's going to speak under the title Group Actions on One-Dimensional Manifolds, a list of very concrete open questions. Please.
Okay. Thank you very much for the introduction. So, I'm very glad to be here in Rio de Janeiro giving this talk. This was my home for many years in my career. So I think that the first thing that I have to do here is trying to justify myself. Why I'm giving a talk in this session of dynamical systems, because I will speak about groups. And I choose two ways to do this. The first is a kind of authority argument. I will just quote Poincaré. Okay? Poincaré said this at some moment of his career. So mathematics is something just concerning about groups. And I think we will not disagree with Poincaré here because, you know, Poincaré is the father of all of us here. Okay? But more seriously, and this is the goal of my talk, is trying to convince you that groups are dynamical objects. And for that, I will come back to the definition of a group. I mean, I will not give the definition, but I will try to explain a little bit this point. So usually, groups in algebra courses are introduced as a kind of very abstract object. It's a set endowed with a multiplication rule which satisfies certain properties, certain axioms. And well, this definition was made clear by Cayley, starting from the work of Galois. But Cayley himself proved a remarkable theorem, which is a kind of trivial theorem, but which is very important and reveals some of this insight. So Cayley proved that every group is a group of automorphisms of a certain space. So every group can be realized actually as a group of automorphisms of the group itself. So, and the proof everybody knows is a kind of trivial proof. You just make the group act on itself by left translations, okay? And actually, you can put some geometry on this proof. You can, if your group is finitely generated, then you can consider the Cayley graph of the group, which is just the graph where the vertices are the group elements, and you connect any two elements if they differ by right multiplication by a generator. And then this action, the Cayley action, becomes an action by isometries of this space. So for instance, this is the Cayley graph of the free group with the canonical generators, which I prefer to see this way because this is the realization inside the hyperbolous disk, and this way you can realize the Cayley action as an action by isometries of the Poincaré disk. Okay, but the key point is that, groups are the mathematical object that act. And whenever you have an action, then you have a dynamics. And this is the reason why groups should be considered also as dynamical objects. Okay, and there is a general principle actually in group theory which says that if you have a group and you want to understand the group, even the algebraic structure of the group, one thing you can do is try to make this group act on some space. And if you have a nice action on a nice space, then this is for sure you will get a nice theorem for the group or for the class of groups. But actually, there is a second point in this talk, and the point is that even when you think about classical dynamics, I mean diffeomorphisms or vector fields or flows, it is sometimes useful to think from a group theoretical perspective. And this is widely known. For instance, when you look at the dynamics of a single diffeomorphisms, it is sometimes useful to look at the centralizer of the diffeomorphism. And in some cases, for instance, in the one-dimensional case or in the hyperbolic case, it turns out that this centralizer is an abelian group. And this gives some information, at least at a differentiable level, of the action of the element, of the action of the diffeomorphism you want to understand. Okay, now I will try to realize these actions as actions on, say, spaces which are more familiar to us. So, for instance, this is a canonical space where every group acts. So every group acts on the Cantor set. Every group can be realized as a group of homeomorphism of the Cantor set. And this is somehow a more dynamical view of Cayley's proof. So you just take 0, 1 to the gamma. If gamma is infinite, then this is a Cantor set, and gamma acts on this space just by shifting coordinates. So there is a shift action, and this way you can realize every group as a group of homeomorphism of the Cantor set. And since my goal is to state a few questions on this, so here is immediately a question. So what are the groups that can be realized by isometries of the Cantor set with a certain metric? Or what are the groups that can be realized at diffeomorphism of the Cantor set with a good differentiable structure on the Cantor set? So this is not a concrete problem. This is just actually this is an area of research. This is not very well understood, actually. Okay, so this realization works very well when gamma is infinite. I mean, when gamma is infinite, this is a Cantor set. If gamma is finite, there are many ways to make finite group act on the Cantor set, but one of the most beautiful ones is related to a remarkable group which was introduced by Richard Thompson in the 60s, I think, or in the 70s. And, well, essentially, Thompson's group is a group of, so you take the Cantor set endowed with the binary structure. So you look at the Cantor set as the boundary at infinite of a rooted dyadic tree, and you look at the homeomorphism, which is piecewise binary, which piecewise dyadic, which means combinatorially to that you take any pair of rooted tree which are finite and which have the same number of leaves, then you permute the leaves, and then you look at the boundary and you realize this permutation as a homeomorphism of the Cantor set. This gives you a group. This is a group of homeomorphism, actually of diffeomorphism of the Cantor set, if you wish. And this group is really remarkable, and it's a central object on this stuff. So this group, actually it is a finally presented group, which is something very, very impressive. So there are finitely many generators, and there are finitely many relations in the group, from which every relation can be deduced. And it is easy to see that it contains every finite subgroup, every finite group. So every finite group embeds into this group. So it embeds into the group of homeomorphism of the Cantor set. And you can say many things about the algebraic structure of this group by looking at these dynamics. For instance, you can describe the group of automorphisms. In general, when you have a group, one way to understand the group is to understand the automorphism of the group. And it turns out that when your group can be realized dynamically, automorphisms also come from a certain dynamics. So for instance, in this case, this is a theory of Rubin, says that if you have an abstract automorphism of the group, then this is realized by the homeomorphism of the Cantor set that normalizes the action. And you can see a few other things. This is work in progress with Blake, Cameron, Lanoux, and Jonah. And, well, there are two remarkable subgroups of this group. One of these is the subgroup where you made by the element that preserve the cyclic order on the Cantor set. So the Cantor set has a natural cyclic order, and the elements that preserve this cyclic order form a group, and this is the Thompson's group T, and you can realize naturally this group as a group of homeomorphism of the circle, because somehow you can collapse the Cantor set, you can collapse every connected component of the complement, although there is no complement here, but anyway, I think you understand what I am saying. And then this way you get a circle and you get a group of homeomorphism of the circle, which is actually a group of piecewise linear homeomorphism of the circle, and piecewise dyadic homeomorphism of the circle, and it has similar properties to Thomson's group V. It is a finite represented group, and it is also a simple group. And there is another remarkable group, which is the subgroup made by the element that preserve the linear order on the Cantor set, which can be, again, naturally realized as a group of homeomorphism of the interval. And this is Thomson's group F, and I cannot proceed further. Well, this is a presentation, an explicit presentation of Thomson's group F with two generators and two relations. These are the generators. These are two maps realized as homeomorphism of the interval. And there is a central question here, is whether or not this group is amenable. So this has been open for, I think, for 40 years. And this is a kind of nightmare for our community, because every criterion for amenability fails for this group. So this is an open question. Let me just remind that what is amenability. So when we have a continuous map on a compact space, there is a classical theorem by Bogoliubov and Krylov, which says that there is an invariant probability measure. So one way to introduce amenability is saying that for every action on a compact matrix space, if you wish, there is an invariant probability measure for the action. And in general, these are small groups. For instance, it is not hard to see that abelian groups satisfies this property. If you have an action on a compact space, then there is an invariant probability measure. So this is a very important question in this stuff, but actually, and the answer is unclear. I think nobody wants to conjecture nowadays what should be the answer, okay? But there has been remarkable progress over the last year concerning this, at least to understand the question. And in particular, there is a wonderful work by Tim Justin Burr and Josh Loda, who built a closely related group to this group and proved non-amenability using ideas coming from ergoic theory. And, they proved non-amenability using a clever remark by Nicolas Monod, which came back to the work of Gis and Yves Carrière. And what they did was to isolate a particular group which were able to prove that it is finally represented using ideas from combinatorics. So this is really a fantastic work. Okay, so this is dimension 1. So let me go further and pass to dimension 2, and I will try to illustrate how quickly you can go into open question in this stuff. And you can ask interesting questions which are seemingly quite elementary, but for which we don't know the answer. So this is related to Burnside groups. So what is a Burnside? What is the Burnside question? So long time ago, Burnside asked whether if you have a finitely generated group, for which you know that every element has finite order, so it's a torsion group. Every element is torsion, whether this group has to be finite or not, okay? And he proved that the answer is yes, at least for linear groups. And he left open the question for general groups. And to deal with this question, he introduced a family of very natural groups, which are the so-called Burnside groups. And the Burnside group, say in two generators, is just a group generated by two elements, where you impose the condition that every word in A and B, up to the power n, is equal to the identity. So you impose torsion in the group. So this is the presentation of a group. Of course, this is an infinite presentation, because you have infinitely many words, hence you have infinitely many relations here. But this is a group, okay? This is a kind of universal torsion group in which every element has order n or smaller than n, okay? And it is not very hard to see that B2 and B3 are finite groups. This is actually true for B4 and B6. So here the picture is the Cayley graph of B3, I think. It's a group of 27 elements, and this is the Cayley graph with respect to this system of generators, A and B. But it is an open question whether, for instance, B7 is an infinite group, okay? It should be infinite, so according to Gromov, this is obvious, it should be an hyperbolic group, but this is still an open question, okay? And actually, according to Selmanov, B5 should also be infinite, but this is a different kind of question. So I mean, this is, at least for me, this is somehow natural, okay? When you pass from 6 to 7, then you go into the hyperbolic world, so it should be somehow natural. This is something that I have no intuition on this, but anyway. But what is important is that there is a theorem, and the theorem says that for n large enough, at least larger than this number, I think, Bn is infinite, okay? It's an infinite group, and actually, it is non-amenable. This is a theorem proved by Adiana and Novikov in the 60s. It's a very important theorem, okay? Okay, so let me now state the question. This is a very elementary question that I learned from many people, and it's a kind of folklore question in this stuff. Assume now that you have a group gamma of homeomorphism of the sphere, of the two sphere, and you suppose that every element is torsion, and your group is finitely generated. Must the group be finite? Can such a group be a Burnside, a counterexample to the Burnside question, to the Burnside conjecture, actually? Okay, so this question is open, okay? And this question is very nice. So let me just explain something about this. So I am asking this question in dimension 2 because in dimension 1 this is trivial. The answer is yes, and this is really an exercise, okay? But if you go to dimension 2, nobody knows what to do. Actually, you can ask the same question for any surface, but the work of Gelman and Lewis somehow reduces the general case to the case of the sphere. This is the difficult case. And why this question is nice? Because, you know, there is a classical theorem by this guy, Kierekjarto. So, okay. I am unable to pronounce this name, but anyway. Kierekjarto proved using ideas of, the Brouwer theory, classical two-dimensional topological dynamics, that if you have a finite order homeomorphism of the sphere, then you can change coordinates, and what you see after the change of coordinates is a rotation. So every finite order homeomorphism of the sphere is topologically conjugate to a rotation. So this question means that whether there could be a group for which every element is up to a change of coordinates, a rotation, but the group itself is not a group of rotations up to change of coordinates, okay? And the answer is unclear, and let me stress why. At least for me, it's unclear. It is because in dimension 1, there are very nice examples constructed by Natasha Kovacevic. She built examples of group of homeomorphism of the circle, such that every element is conjugate to a Möbius map, but the group itself is not conjugate to a group of Möbius map. And this is something very, very striking, And one can realize some of her examples actually as group of diffeomorphism of the circle. So it seems that there is no issue concerning regularity here. But let me say that there has been a great progress towards the solution of this question. This is the work of Sebastián Hurtado. And adding some extra hypotheses, he managed to prove that every torsion group of homeomorphism of the sphere is actually finite. So what are the hypotheses? So first of all, he assumed smoothness. So he assumed C-infinite diffeomorphisms. I think C2 is enough. He assumed that the maps preserve the area. Somehow, area-preserving diffeomorphisms are easier to handle than just diffeomorphisms. And there is an extra hypothesis concerning the torsion. So he assumed that the order of group elements are uniformly bounded from above. So somehow what he's looking at are actions of Burnside groups. So under these three hypotheses, he proves that groups must be finite. And this work is really very nice because you have to split into 3 cases. There is a hyperbolic case where you using ideas from the, differentiable dynamics, you are able to detect hyperbolic fixed points, which are in contradiction to torsion. Then you have to look at the case where you have no hyperbolicity at all. When you have no hyperbolicity and the group is small, somehow you can conjugate into group of rotations. And if you have no hyperbolicity but your group is large, then you have too many orbits. So you have, and when you are in dimension 2 and you have orbits which are small, then you are able to detect fixed points using the ideas of Brouwer theory. So this is somehow how it works. And there is a nice counterpart of this by Jonathan Conejeros, who proved more or less the same thing without the differentiability hypothesis, but using a very strong hypothesis on the exponent. So he assumed that the exponents are power of 2. This is a natural hypothesis for this problem because rotation can have any order, but what is nice is that this proof is totally elementary. Okay, so you see, this is a very natural and elementary question, and we don't know the answer. And this is the point. When we want to pass, we want to go further in dimension, we still lack of a general theory of a structure of groups of diffeomorphisms. This only exists in dimension 1. This doesn't mean that there are no progress on this stuff. Actually, there is a remarkable progress in relation to the Zimmer conjecture by Brown, Fisher, and Hurtado, but we still lack of a theory, of a good framework to deal with the structure of general diffeomorphisms group. So I will come back to the case of dimension 1. And what is nice here is that in dimension 1, even in the case of homeomorphisms, there are a lot of rigidity phenomena that do not appear in higher dimension unless you put some hypothesis of differentiability, and that do not appear in the context of single maps, because single maps acting on one manifolds are very easy to understand from a topological point of view. But if you have group actions, you have a lot of interesting phenomena. So let me just start by saying one thing. So since we are in the continuous setting, actions on the real line and actions on the interval are the same, and you can characterize the existence of an action by a algebraic property of the group. And the characterization, or I mean the translation into that language, is the existence of a left order in the group, which means a total order on the group which is invariant under left multiplication. Okay? And then you make a bridge with a theory which was developed by people from algebra starting from the 50s, actually before, because even Hölder was interested in this kind of things. And it is very interesting to make this bridge between dynamics, algebra, this is pure algebra, and actually with foliation theory. So let me just quote one of these famous and quite, say, sarcastic review by Giancarlo Rota of the book of Kokorin and Kopitov, which is a kind of classical reference for order groups. So he said that for some unexplained reason, some people like to linearly order groups. Even more mysteriously, most of these people work in the Soviet Union. And actually, they had a great school of people dealing with this. But actually, in some sense, he's right, because they were dealing with very deep questions. Actually, in this book, one can find, as an example, the Thomson's group that appeared, I think, later in the West. But they were doing a very good job, and it was a nice stuff trying to restate all this job which was made in an algebraic language into in dynamical terms, which is given by this, say, by the dictionary here. And if you go instead of considering actions on the real line, you consider actions on the circle, then there is a similar dictionary. Now the algebraic condition is stated in terms of bounded cohomology. Bounded cohomology, which coefficient in C having certain representative, but, well, this is in complicated words, just saying that there is an analogous of the point carrier rotation number theory in the case of group actions, at least for groups without a finite orbit, okay? And this was a remarkable work of Gis in the 80s, I think. Okay, so you can characterize algebraically groups that do act on one-dimensional manifolds. And again, this motivates very elementary question, okay? So that's there exists an algebraic characterization of groups that act faithfully by homeomorphism of a manifold, of a two-manifold. Can you say a priori that a given group acts by homeomorphism of the sphere or not? We don't know whether this property is algebraic or not, okay? Okay, so the question is not very clear, but let me state a more clear question. So this is a kind of chain for us, okay? Does there exist a torsion-free group, finitely generated, which cannot be realized as a group of homeomorphisms of a surface? So nobody knows such an example, okay? In dimension 1, it's very easy to realize these kind of things. I mean, not that easy, but in dimension 2, nobody knows of any single example. And here is another question. So does there exist a group that cannot be realized as a group of homeomorphism of a two-manifold, which is the limit of groups that can be realized as group of homeomorphisms? Limit in the sense of Gromov or Hausdorff or Chabot, whatever you like. So limit means that you take the sequence of group associated to each group, there is a Cayley graph, and you say that the sequence of group converges to the limit group if the sequence of Cayley graphs converges to the Cayley graph of the limit group in the Chabot topology, or in the Gromov-Hausdorff topology, okay? Again, we don't know. And what is interesting here is that the answer for this question is yes. No, it's no. It doesn't exist in dimension 1 because the algebraic condition is somehow robust. If you have a sequence of groups which are left orderable, then the limit group will be left orderable because this condition is a compact condition in some space, if you wish. And the same for the property expressed in terms of bounded cohomology. And there is another concern about one-dimensional actions in the topological level, which is something very interesting, which doesn't arise for single map, but which appears for the case of group actions. So this is related to structural stability. So let me give an example. So I will consider break groups. So break groups are known to be left orderable by a very important theorem by Patrick de Hornoy, for which there is an alternative proof by Thurston using the action on the hyperbolic action, if you wish. Okay, so break groups are left orderable. They can be realized as group of homeomorphism of the real line, and I will consider the following thing. So B3 is the group generated by two elements, sigma 1 and sigma 2, satisfying the Bray relation sigma 1, sigma 2, sigma 1 equals to sigma 2, sigma 1, sigma 2. This is the definition of the Bray group. And I will suppose that this element A, which is the product of sigma 1, sigma 2, and B, which is the inverse of sigma 2, move a point to the right simultaneously. When you have such an action, with this condition, then you know the action. Okay, this is quite amazing. But the point is that there is something very simple which is happening at the level of left orders on the group. What happens is that there is a particular left order on this group which is totally determined by the condition that the A is larger than the identity and B is larger than the identity. Okay? And this translates into this language of structural stability. So every action satisfying this property is up to topologically semi-conjugacy equal to some standard action. Okay? And here, semi-conjugacy means that you can, in the continuous setting, you can always do, say, the Danjoatric opening orbit, so the blow-up orbit, okay? And there is a, well, this is a kind of local structural stability, but in the case of the circle, there is another example which is really quite striking. There is a group which is globally structurally stable. So this is Thomson's group T. The Thomson group that acts on the circle, it has a unique action on the circle. There is no way to make it act on the circle in a different way. So every action is semi-conjugate to the standard action. So this is a structurally stable group of homeomorphisms, okay, which is quite remarkable. I mean, well, again, a question. Does there exist a group of homeomorphism of a two manifold which is structurally stable? We don't know. Now, if you impose some regularity, the situation changes a lot. Because, of course, you can use the regularity to say a few things. There is some rigidity that arises in a different context. And actually, this has been a study by people coming from foliation theory, especially. They were somehow inspired by Danjois theorem, which is a kind of fundamental theorem in this stuff. And this has been parsed by many people, but I will give my favorite theorem on this stuff, which is a kind of brilliant theorem. I mean, the proof is really brilliant, and even more than the proof. So Thurston was extremely clever to detect this phenomenon. So the theorem is the following. Take a group of C1 diffeomorphisms of the interval. Actually, you can take a group of C1 of germs of C1 diffeomorphism at the origin, okay, and it works. And if you assume that the group is finitely generated, then there is a homomorphism from this group into the reals, okay? And this gives an algebraic constraint of group of C1 diffeomorphisms, which doesn't arise in the context of homeomorphisms. And the proof is very natural. So for the proof, you just take the derivative at the origin, and then you take the logarithm of the derivative. And because of the chain rule, this is going to be a group of homomorphism. This is clear. Okay, this is the proof, except for one thing. It may happen that this homomorphism is trivial. Okay, this homomorphism could be trivial. Actually, it may happen that all the elements in the group are infinitely tangent to the identity at this point. And what Thurston does is somehow to renormalize the geometry close to the fixed point in order to detect the good scales where you see some derivative. Okay? And this is the Thurston homomorphism. This is really amazing because the only thing that you use for the proof of this is the definition of the derivative. This is really remarkable. Okay? And for many years, this was the only abstraction which was known to be C1 smoothable, but actually there are more abstractions than this. So if you see, okay, prior to this, let me give an example. So this theorem applies to finitely generated group of diffeomorphisms. So if you have a group, it applies to every finitely generated subgroup. So this is a kind of local property. You say that you have a local property when it applies to every finitely generated subgroup. So this theorem says that the group of C1 diffeomorphisms of the interval is locally indicable. So every finitely generated subgroup maps onto C, if you wish. And here is an example which is actually in the paper of Thurston from the 70s, which is the following. So you take the 2, 3, 7 triangular subgroup of Pesel 2R. This is the subgroup of Pesel 2R of the element that preserves the styling. So this group acts on the boundary. So this is a group of circle homomorphism. And then you take the lift to the real line. So it's another group. It's an extension of your group. And doing some computation on the presentation of this group, you see that there is no homomorphism into R. However, this group acts on the covering of the circle. So it acts on the real line. So it's a group of homeomorphism of the real line which is not realizable as a group of C1 diffeomorphism of the interval. However, in that case, the abstraction is localized at the end point of the interval, at the origin. But there are many other abstractions which have been discovered by myself, and especially in collaboration with Bonatti, Monteverde, and Rivas. So local indicability is not the only abstraction to C1 smoothness, okay? And actually, you can localize the abstraction everywhere, okay? There are even solvable group of homeomorphisms that cannot be realized as group of diffeomorphisms. So the situation is unclear for C1 smoothings. Now, if you want to go further, you can consider, say, C1 plus alpha diffeomorphism. So it is very well known that the dynamics of C1 diffeomorphism and C1 plus alpha diffeomorphism can be very different, for instance, in the setting of hyperbolic dynamics. So this is the definition of what is a C1 plus alpha diffeomorphism. Is a diffeomorphism for which the derivative satisfies a Holder condition with exponent alpha. And here is a concrete result in this direction. So there is a group of C1 diffeomorphisms, which is very special, which cannot be realized as a group of C1 plus alpha diffeomorphisms. And this is related to some kind of hyperbolic behavior, but not from the dynamics, but coming from the group. So the theorem says that every finitely generated subgroup of the group of C1 plus alpha diffeomorphisms have either polynomial or exponential growth. So the growth means the following. So you have a finitely generated group, and you count the number of elements that may be written as products of no more than n generators in a prescribed system of generators. And you look at this function as a function of n, and you look at the behavior of this function, okay? If this function grows exponentially, then you say that the group has exponential growth. And if the behavior is polynomial, then you say that it's polynomial, etc. And there is a very important theorem essentially by Gromov, which says that polynomial growth is equivalent to being nilpotent up to a finite index, okay? So this theorem, what says is that groups with intermediate behavior, namely group of intermediate growth, cannot arise as group of C1 plus alpha diffeomorphisms, although they can appear in the group of C1 diffeomorphisms. And since I like to ask questions, let me say that this question is widely open again. Does there exist a group of intermediate growth of diffeomorphism of the sphere? Even real analytic, we don't know. Okay. Even area preserving, we don't know. Okay, let me give the example of the group, because you will recognize some issues coming from one-dimensional dynamics. So the example is very nice. This is an historical example. This was the first example of a group with intermediate growth. It was constructed by Grigorchuk, and it's a group generated by 4 elements. So here, what we have is the binary root tree, and this group is realized as a group of automorphisms of this tree. And here are the generators, A, B, C, and D. So A is just an order 2 element. It's just the permutation between left and right. And B is an element that fixes the first 2 levels. So it fixes this vertex here and this vertex here. And starting from here, what you see is another binary root tree, and the action of B on this tree mimics the action of A. So here there is a permutation of order 2 between these 2 branches. And the action of B on this subtree here mimics the action of C. So we have to pass to the definition of C. And the definition of C is, again, by recurrence. So on the left, you mimic the action of A, and on the right, you mimic the action of D. And now we have to define D. So on the left, you have to put the identity, okay? And on the right, you put the action of B. And there is no contradiction in this definition, because you are going into deep into deeper level. So at the end, what you get is a group of automorphism, or if you wish, is a group of homeomorphism of the Cantor set. And it turns out that, well, doing some complicated stuff, one can prove that this group is far away from being nilpotent, but it is too small to be of exponential growth. In particular, if you have any two elements, you can find relations between these elements in which the powers of the elements that appear are only positive. So there is no free subsemigroup inside this group. Okay? So this is another way to introduce this group. This is kind of arithmetic way to introduce. This is the same action on the Cantor set. And now what Grigorchuk did together with Maki was to replace this construction, changing by the binary tree by a linearly ordered tree. So I will change the Li here, which come from 0 and 1, by Li, which come from the integers. And instead of taking permutations, I will take translations at each level. So you have a tree in which the valence of every vertex is infinite. And you see translation dynamics at every level. And then the boundary at infinite, you can consider, instead of being a Cantor set, you think of as being an interval. And you see some dynamics there. And then you try to realize this in a smooth way. And there is something that naturally comes in mind, is the Danjois counterexample, because you have to glue together many diffeomorphisms. And this is what is done. This can be done, but it's a little bit technical, because, you know, a Danjois counterexample exists in any differentiability larger than C1 but smaller than C2. And here the best you can do is C1, because of the theorem. In class C1 plus alpha, there is this dichotomy between exponential and polynomial growth. Okay, actually the dichotomy is even stronger. You have either polynomial growth or you have the existence of free subsemigroups inside the group, which is stronger than just being exponential growth. And you can pursue this analysis to, say, to small groups. So here there is a fundamental work by Tsuboy, who realized that there was a very deep connection with kind of cohomological aspect of group theory and foliations. But here I prefer to report on this theorem by these two guys, Sam Kim and Thomas Coverda, who recently managed to prove something quite impressive, at least for me. So this was an open question for many years. So I asked this question more than 10 years ago. And I think that Tsuboy also asked the very same question even before. And well, the theorem is the following. If you take any two differentiabilities R and S, which are not necessarily integer numbers, but which are at least equal to 1, then there is a group of diffeomorphism of class CS that cannot be realizable as a group of diffeomorphism of class CR. So just by looking at finitely generated subgroups, you can detect the differentiability class of the differentiability structure of the one manifold. This is really a fantastic theorem. The proof is really wonderful, because all these groups appear as quotients of the same group that they were very clever to detect. And let me explain something. So there are two issues here. So the origin of this question comes from a very important work by Jenny Harrison. So Jenny Harrison in the 70s constructed diffeomorphism of two manifolds, actually any manifold dimension larger than 1, which are not smoothable. So you cannot conjugate into diffeomorphisms. You have diffeomorphism on this manifold which cannot be topologically conjugated into diffeomorphism of better regularity. But the case of dimension 1 was special because, and this is the content of, part of the content of the Danjois-Poincaré theory, if you have, say, a circle diffeomorphism of irrational rotation number, then it is topologically conjugated to the rotation. So there is no room to discover nice things for the case of single maps. But this kind of thing can appear for group actions. This is what is why this is really nice. And the other thing is that you really have to impose this condition here because there is a single reality phenomena which appears in the thesis of Bertrand de Rouen, and then we grew up with de Rouen and Clebson, which is if you take any group of homeomorphism, you can conjugate into a group of Lipschitz homeomorphisms. In general, this is the best you can do. And this is, again, a one-dimensional phenomenon. There is nothing like this in higher dimensions. Okay? And, well, and here is an important point. When you have derivatives, when you have group of diffeomorphisms, what happens is that the derivatives, you can take the classical derivative or the affine derivative or the transient derivatives. Derivatives are cocycles. So they suit very well when studying group actions. And this was realized in the context of codimension 1 foliations for the first time by Saxteder, who proved some generalization to group actions of the Andrés theorem. Okay? And just to finish, let me report on this. So this is a theorem that was recently published that we proved with de Rouen and Clebson that solve a long-standing question in this area. Except for that, we have some extra hypothesis, but anyway. So the question was whether or not groups of circle diffeomorphism behave like Möbius groups, okay? And this is a general philosophy on this stuff, okay? And here we have detected some issues concerning this. So if you have a group of diffeomorphisms over the circle, and if there is a Cantor set which is invariant, and on which the dynamic is minimal, like limit set for Fuchsian groups, then the Lebesgue measure of this set is 0. Moreover, if you look at the complement of the Cantor set, then this can be the set of orbits decomposed into finitely many orbits. The set of connected components of the complement decomposed into finitely many orbits. So this, for the case of Fuchsian groups, these are classical theorem by Alfors, and now they extend to general group of circle diffeomorphisms, at least in the real analytic case. And besides, in the case where the action is minimal, there is something that happens that comes from the fact that we are dealing with a one-dimensional space, is that automatically the action is ergodic with respect to the Lebesgue measure. Okay? So this was a conjecture by Gies and Sullivan. This was also a conjecture by Gies and Sullivan. This was a conjecture by Hector. So the point here is that this is false. This is widely known to be false in dimension 2. So in dimension 2, there are classical examples by Furstenberg of minimal homeomorphism of the torus, which are non-ergodic. Actually, minimal real analytic diffeomorphism of the torus, which are non-ergodic with respect to the Lebesgue measure. But something like this cannot happen in dimension 1. And so this is, just to finish, this is a general philosophy on this stuff. In general, groups of circle diffeomorphism behave like Möbius groups in a certain sense. This is, in general, when you want to detect something interesting, then you look at the case of Möbius group, and then you try to generalize this behavior to general group of diffeomorphisms. So I will skip this. Let me just finish with this with this result by this as a kind of comparison. So for Fuchsian groups, there is a classical inequality by Jorgensen, which says that if you have a Fuchsian groups, I think in the old terminology it was called of second category. So it's a Fuchsian group with a limit set with a Cantor set, which is a Cantor set. Then this Fuchsian group is very special. It cannot be generated by elements which are too close to the identity. Okay? And there is an equality, an explicit inequality in terms of traces of the corresponding matrices. Okay? And for the case of groups of diffeomorphisms, there is a counterpart, which is a theorem by Gerard Dumini, which says the same thing. If you had diffeomorphism of the circle, which are very close to the, say, to rotations in the C2 topology, then they cannot generate a group with an invariant Cantor set. Okay? And actually, one can give a very concrete a statement of this theorem, a very precise statement, at least for the case of Jorgensen theorem. So if you define, if you consider this measure of nonlinearity of the diffeomorphism, so the variation, the total variation of the logarithm of the derivative, so this is a very nice formula that we discovered with Adolfo Guillot, although we never wrote anything on this. So when you have a Möbius map, you have some distortion inside of the Poincaré disk, and you have some distortion on the circle, on the limit circle. And these are related by this formula. So the total variation of the diffeomorphism of the circle equals four times the displacement of the map at the origin. So 4 times the distance between the origin and its image, okay? And using this formula, one can realize using just the work of Yamada on systoles of hyperbolic orbifolds that the optimal statement for the Jorgensen inequality or for Dumini's theorem restricted to Pessel to R is the following. So if you have a subgroup of Pessel to R generated by elements for which the total variation of the logarithm of the generator is at most 4 times log of phi over 3, then this group cannot generate, then the group which is generated cannot preserve a Cantor set of the boundary. So, and this is optimal. So there are examples, actually Pessel 2C is an example of a group which may be realized as a group having a Cantor set for which the variation of the logarithm of the derivative of generator is slightly larger than this number. So this is an optimal bound, and this comes from the work of Yamada on Marsden constant for systoles of orbifolds. So I think I will stop here. Thank you very much.
Okay. So, thank you very much for wonderful presentation. Because we are in a bit behind the time, so maybe I ask you to give a question personally later. So, so thank you again for the